This is video number 2 in our dynamics notes for Mr. Sweeney's AP Physics C class. And in this video, we're going to discuss Newton's second law of motion. Newton's second law of motion states that the acceleration of an object is directly proportional to the net force applied and inversely proportional to an object's mass. So when objects change their velocity, one factor is how hard they're getting pushed, the other factor is how much mass they have. This can be written as the equation force equals mass times acceleration. This equation itself, F equals ma, is one of, if not the most significant equation we'll look at all year long. Symbolically, F is for equivalent to force, and that's given in newtons. M is mass, and that's given in kilograms. And A is acceleration, that's given in meters per second squared. When we're trying to solve a forces problem, F equals ma, we still want to work with our free body diagrams. So our first step is drawing a free body diagram. This may not be necessary if there's only one force acting on your object, and if that force is already acting in the vertical or horizontal direction. Once we have our free body diagram, we want to make sure that any of the forces that are not on the x or y axis are resolved into their components that do lie on the x and y axis, so that way on our free body diagram we're working with no more than 2 dimensions of forces. Once we have our forces in 2 dimensions, a vertical and a horizontal, we can write expressions for the net force in the x and y directions. We set these forces equal to ma. So net force in the y, net force in the x, both are equal to mass times acceleration. Typically they'll only be moving in one of those 2 directions. And then we solve net force equals mass times acceleration. So it's very, very important that we use our free body diagrams to determine net force, that we use this net force in net force equals mass times acceleration. Let's try a couple of examples of problems using these ideas. The first one says that there's a net force of 15 newtons acting on an encyclopedia, causing it to accelerate at a rate of 5 meters per second squared. We want to know what the mass of the encyclopedia is. So we use the equation force equals mass times acceleration. We plug in, Lucy, hey. We plug in for force, 15 newtons, equals mass, and our acceleration is 5 meters per second squared. And using this, we solve for our mass, which is 3 kilograms. And it makes sense, 3 kilograms times 5 meters per second is 15 kilograms meters per second squared, which is equivalent to a newton. In the second example, we have a 150 gram golf ball that's driven forward by a 6 newton force. We want to know how fast is the ball accelerating while it's been driven. Again, we use force equals mass times acceleration. Our force is 6 newtons. Our mass, 150 grams, equivalent to 0.150 kilograms, yields us an acceleration. 6 divided by 0.15 is 40, an acceleration of 40 meters per second squared. So those 2 are very basic F equals ma equations. If we're looking at a calculus-based type equation, we'll first do it symbolically. And these generally include equations that are given to us, kinematic equations that we're applying, trying to find the acceleration of, then applying F equals ma to that. In this example, a particle with mass m moves along a straight path with a speed v as defined by the function v equals bt squared plus ct, where b and c are both constants and t is time. I want to know what the magnitude F is of the net force of the particle at time t equals t1. So we have a velocity expression. And to find force, we need to have acceleration times mass. So the first thing we have to do is we have to rewrite this expression for velocity and instead take the derivative of velocity, which will give us acceleration. So doing this, we find that the acceleration equals 2bt, which is the derivative of bt squared, plus c, which is the derivative of ct. We know that mass equals, or force equals mass times acceleration, so we multiply 2bt plus c times mass to find an expression for the force at t1. Force equals 2btm plus cm, and the c being the constant, m being the mass. So this is symbolically. Down below, we can solve for a problem that gives us an expression. In this example, it says a 0.340 kilogram particle moves in a straight line according to the equation position equals 4t cubed minus 2t plus 15. I want to know what's the net force of this object at t equals 7 seconds. Similarly to our last problem, we have an expression or an equation that relates time and position. And acceleration is the second derivative of position. So we'll take the first derivative and find that velocity of time equals 12t squared minus 2. Or 12t squared is 4t cubed, the derivative of that. 2t, the derivative of that is 2. We can take the derivative of this function to find acceleration, and that acceleration is 24t. Now this relates time and acceleration. We know at time equals 7 seconds, we can find what the acceleration is. At 7 seconds, it's just 24 times t. 24 times 7 is 168 meters per second squared. At that moment, 7 seconds into its motion, it's accelerating at this rate, which is a tremendous rate. Finally, we can say that force being applied to it is equal to mass times acceleration. Our acceleration is 168 meters per second squared, and the mass being 0.34 kilograms. So 168 times 0.34 yields us a force of 57 newtons. This is it for our notes on Newton's second law.